Hello, everyone, and welcome to your third lesson in Unit 7, where we're going to be talking about bond energy. And this really is a continuation of the idea of enthalpy and heat and all of that good stuff. We're just going to add a piece, which is bond energy. So why do I have Lewis structures? That's because most of the time, in order for us to know exactly how many bonds and what elements those bonds are between inside of a molecule, we're going to have to draw it out. Now, good news, a lot of times if they're complicated molecules, they give it to you drawn out if they're asking you to do bond energy. Bad news, eventually in a later unit, we really do have to know the ins and outs of how to draw a Lewis structure, because that's a whole nother topic that is assessed on the AP exam. So I'm not going to go as in depth into Lewis structures right now, because most of the time for the purposes of using bond energies in this unit, it's going to be either very simple molecules or they're going to be drawn out for you. However, I'm going to do a quick overview of Lewis structures so that you're not totally lost when it comes to determining the number of bonds and the types of bonds in molecules. So Lewis structures just show valence electrons, so they only show the outermost electrons in an atom or atoms. Generally, something to remember, atoms obey what we call the octet rules, so having 8 electrons is considered stable. They're kind of trying to get to that noble gas configuration. So an atom can either have lone pairs, which means 2 electrons that are not inside of a bond, or they can share an electron, which is 2 electrons inside of a covalent bond. What these 2 chlorines have done now is they each have 1, 2, 3, 4, 5, 6, 7, 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8 electrons. So by sharing that, they now have each 8 electrons around them. That's what we mean by that octet rule. Now we do have some exceptions. Our first couple of elements can't quite hold 8. And so, for example, boron is satisfied with 6 electrons. And then we have some really big atoms that can actually expand their octet. Again, at this point, we're not going to go so much into how that happens and all these different exceptions. We're just trying to look at the basics. So drawing Lewis structures is something that a lot of students, if they remember it from honors, they remember it as being really, really hard or confusing. And I think a lot of times that comes from not having kind of a set of steps that you can follow to draw your structure. So if we have super simple molecules where we can easily see where we can just match them together so that everybody has a full shell just by sharing lone electrons. So for example, here we have 2 hydrogens, each with 1. So we're just going to put those on the sulfur, and now the sulfur has 8, each hydrogen has 2, so they're both full. Those are pretty simple. If we have more complicated molecules, we can follow this set of instructions. So first, we're going to determine the total number of valence electrons when we add up all of the elements that are in the molecule. Now, for a refresher, if you don't remember, number of valence electrons is equal to the column that it's in on the periodic table. So, for example, oxygen is in 6A. So if we think of it as 1, 2, then we go over here into the taller columns, 3, 4, 5, 6, 7, 8. Oxygen is in group 6, so it has 6 valence electrons. Nitrogen is in group 5, so it has 5. Carbon is in 4, it has 4, so on and so forth. So you're going to add up all the valence electrons. If it happens to be an ion, you would add or subtract however many. So if it's got a positive charge, you would take off that many electrons. If it has a negative charge, you would add that many electrons. Then you're going to draw a skeleton structure. So you're just going to put the center atom, which is typically your least electronegative or the one that can make the most bonds. So you're going to put that in the center, and then you're just going to connect it to all the outer atoms with a single bond. Then you're going to distribute other electrons as lone pairs on your outside atoms, unless it's hydrogen, because hydrogen can only hold 1. extra electron for a total of 2. And you're going to complete their outer shells, the outside. I'm going to show you an example in just a minute. Then, if you still have remaining electrons to account for, you're going to put them in the center atom. And then finally, you're going to look to see if there are areas where you need to rearrange to make a double or a triple bond to make it the most stable molecule. Now, you're probably wondering why I have this picture here, which is always my favorite when this comes during basketball season. So there used to be tons of t-shirts that were made like this. They had all different types of things, but I had one that was Carolina and Duke. And so I like to use this as an example. So electrons don't like to be alone. So no electron wants to be this sad little Duke fan. Okay, so electrons like to be in a pair. And that pair can either be that lone pair or with another element's lone electron to where now they both are in a pair. So you always want to make sure you're not leaving an electron out. Okay. So now we're going to go through those steps, but we're going to actually do so with examples. So we're looking at 4 examples here. We have SiH4, CHO2 minus, NO plus, and OF2. So the first thing that we need to do is we need to count up the total number of valence electrons in each of these atoms. So silicon is in group 4, it's right under carbon, so it has 4 valence electrons. Each hydrogen has 1, but there's 4 of them, so now we have a total of 8 valence electrons. Carbon has 4, hydrogen has 1, oxygen has 6, there's 2 of them. But then we also have a -1 charge, so I got to add in an extra electron for that -1 charge. So that gives me 4, 5, 6 times 2 is 12, plus 5 is 17, plus 1 is 18 total valence electrons. Nitrogen has 5, oxygen has 6, but a +1 charge means we lost an electron. So 11 minus 1 is 10 total electrons. And then finally, oxygen is 6, fluorine is 7. We have 2 fluorines. 7 times 2 is 14, plus 6 equals 20. So that's how we add up our total valence electrons. Okay. So then we're going to draw our skeleton structure, meaning if we have more than 2 atoms, one of them is going to be in the center. That's going to be your least electronegative atom, or your one that can make the most bonds. So in other words, if carbon, silicon, those are always going to be your center atoms. So silicon's in the center here, carbon, there is no central atom on this one, and then oxygen. And then I'm just going to arrange my other atoms around it. I'm going to connect them all with a single bond. Then I'm going to distribute other electrons, other remaining electrons, as lone pairs around the outer atoms. Now you'll notice that for this molecule, that I didn't add any extra electrons because I have 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. All of my electrons are taken care of for this molecule. Also, we would know we don't add any out here because hydrogen is already full with its 2, 1, 2, the one that it has, the one it's sharing. So that molecule has all of its electrons accounted for. All right, so CHO2 has 18 electrons. Before we started adding, we had 1, 2, 3, 4, 5, 6 electrons. So I'm just going to start filling in the outer elements, not hydrogen because it's already full. 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18. Oh, all of our electrons are accounted for. Now I look at this next one. We have 2. Let me keep going. 3, 4, 5, 6, 7, 8, 9, 10. So that now has taken care of all the electrons. And then for our oxygen and fluorine, we have 20. We started with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We're at 16 electrons. So we are not done, which is why we go to step 4 where we add the remaining ones on the center atom, 17, 18, 19, 20. Now all of our electrons are taken care of. So now we're going to look to see, is every atom have its full octet or its full shell? And if not, we're going to rearrange bonds. So hydrogen and silicon all have their full, so this is the final Lewis structure for that Now let's look at the CHO2. Carbon only has 6 electrons around it rather than 8. So what we see is we can move a lone pair down there. Now carbon has 8, hydrogen has 2, which is full, and then each oxygen has 8, which now they're all full. Now, if you drew this with the double bond on the top oxygen, that is 100% appropriate. We'll talk later on when we get in depth in Lewis structures, what those structures are called. Now, if we look at the fluorine and oxygen one, all of these have 8, so that's the final structure. And then looking at the nitrogen monoxide ion, both of them only have 6. So if I move a lone pair down, now nitrogen has 8, but oxygen still has 6. Now if I move one of nitrogens down, now with that triple bond, both of them have a full valence shell. All right, here are some for you to practice. If I were you, I would maybe pause, try them on your own, and then resume. So this first one, carbon dioxide. Carbon has 4 electrons, oxygen has 6. There's 2 oxygens, so that gives me 12 plus 4, which is 16 total electrons. I'm going to put carbon in the middle, attach it to each oxygen with a single bond. Now I'm going to fill in my outer atoms, which in this case are oxygen. So now I have 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now I've taken care of all of my electrons, but poor little carbon in here only has 4. So what I can do is I can move each of those down, and now everybody has their full octet. Look at the cyanide ion. Carbon has 4, nitrogen has 5, and then we have a -1 charge, so we're going to add in an electron for that. So we have 10 total electrons. No center atom here because there's only 2, so I'm just going to connect them. Now I'm going to fill in the outside. So that's 6, 7, 8, 9, 10. So there I have 10 total electrons. Carbon has all 8, but nitrogen only has 4. So I'm going to move these 2 down and have that double bond, which actually gives me 8 for each of them, that -1 charge. If we have ions, we typically put the structure in brackets so we can put the charge outside of it. Hydrogen has 1, fluorine has 7 valence electrons, so we have a total of 8. So I connect them with a single bond. Again, there's no center atom here because there's only 2. Then hydrogen's already full, but I'm going to fill in fluorine. So now we have 6, 7, 8. We are done. Nitrogen has 5, hydrogen has 1. There's 3 hydrogens. That gives me 8 total electrons. Nitrogen in the middle, I'm going to connect them all to the hydrogens with single bonds. That's 6 total electrons. I have 2 more remaining. I can't put them on hydrogens because hydrogen's already full, so I go to the center atom, which is nitrogen. All of them have their full octet, so we are good to go. Finally, carbon has 4, fluorine has 7, times 4, which is 28 plus 4 is 32. Carbon in the center, connect to all 4 fluorines. That's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Everybody has a full octet. We are finished. Whew. All right, guys. So if you are still paying attention and listening, send me a remind message or an email that says, I love Lewis structures, because the more you say it, the more you will. Okay, so what do all those Lewis structures have to do with thermochemistry? So we're now going to talk about bond energy, which by definition is the amount of energy required to break a chemical bond. So, reminder, energy is absorbed when bonds break, it's endothermic, and energy is released when bonds form, that's exothermic. So the higher the bond energy is indicative of a stronger bond. Okay, so the stronger the bond, the higher the bond energy. So bond energies are going to depend on a lot of different things. It's going to depend on the electron affinity of the atom itself, the size of the atom, the differences in their electronegativity, so how strongly they pull on those electrons, and just the overall structure of the molecule. So the picture I have there is one I'm going to link for you as well, but it just has a bunch of average bond enthalpies. So now, why did it say average bond enthalpy? Well, that's because the bond energies slightly differ, even though they're between the same atoms. So for example, when we look at the methane molecule, which has 4 carbon-hydrogen bonds, the energy required to break the first carbon-hydrogen bond, so let's say it was this one here, is 435. Then the energy required to break the second one is 453, the third one is 425, and then the fourth one is 339. So then what we do is we take an average, and so scientists studied multiple different molecules of the same type of bond and then came up with an average. And then that also means that we can treat a molecule as just a sum of its individual bonds. So the whole bond energy. So for example, each carbon is 413. So we have 4 carbon-hydrogen bonds. So altogether, it's 1,652. So what makes atoms bond in the first place, and then in turn gives them certain lengths and strengths and whatnot? So when atoms are moving closer together, if they're too far apart, there's no attraction. But if they move close enough to be within each other's, space, so to speak, as they get closer, they start to interact. There's going to be attractive forces, which are electron to proton, but there's also going to be repulsive forces. Their electrons are going to repel each other, and their protons are going to repel each other. So what happens as they get closer is they start to attract each other, but then if they get too close, they're going to repel each other, which is, you see down here, we have attraction, and then up here we have repulsion. This is a graph of the energy and then the distance. So what we get to is this kind of Goldilocks distance where the energy is minimized. And so that energy right there is the bond energy. And then from this axis, that's the bond length. So atoms are going to get close enough together where they are more stable bonded than they are apart because the amount of energy to hold them together is minimized. If we have multiple bonds, meaning we have double and triple bonds, that is going to alter the bond length and the bond strength. So single bonds are the weakest, but then they're also the longest. Double bonds are right in the middle, and triple bonds are the shortest and also the strongest. So if we're looking, these are all carbon-carbon bonds, but the energy drastically changes as we go from single to double to triple. So we can use bond energy to actually calculate the heat of a reaction, so that same delta H, enthalpy or heat of reaction, but we're going to use bond energies instead of heats of formation. Now, something you've got to remember, this equation is not given to you on your equation sheet. Now, it's not difficult. It looks very similar to our other ones, but it's not given to you. Here's the big difference. When you are using bond energies, you do reactants minus products. All right? So just stick it in your brain right now. When I use bond energy, I do reactants minus products. Now, why is that? Because we're going to do the energy of bonds broken minus the energy released when bonds form. And so in order to do that, we have to do the bond energies of the reactants minus the products, multiplied by their coefficients, just like all the other, just like the other delta H equation. So let's look at an example. So for this one, I went ahead and gave you the structures. We have hydrogen plus fluorine to make 2 hydrogen fluorides. So if we look in the reactants, we have 1 hydrogen-hydrogen bond. We have one fluorine-fluorine bond. Then in the product, the molecule itself has one hydrogen-fluorine bond, but there are two of them. So when we calculate these bond energies, we are going to look at our table. We have 1 times the HH bond energy, which is a 436. Then we have 1 times the F bond energy, which is 155. Then we are subtracting 2 times the HF energy, which is 567. So when we do that math, we get negative 543 kilojoules per mole. Now, if we calculated that delta H value from heats of formation or using Hess's law, we should get very, very close to 543 kilojoules of energy being released. So this bond enthalpy or bond energy is just another way to calculate enthalpy of reaction. Okay, so let's do some practice here. So you're given the reaction. I always like to draw my structures out just to make sure I don't miss a bond somewhere. Obviously, this one is pretty simple. You also don't necessarily have to draw your lone pairs because it's only the bonds that we're looking at here. So for example, if you left HCl like that, no problem. The important thing here is that we have one HH bond, one chlorine-chlorine bond, and then two, because of the coefficient of 2, hydrogen-chlorine bonds. Now, with bond energy, it's reactants minus products. So I'm going to do the sum of the reactants. I have one hydrogen-hydrogen bond, which is 436, plus one chlorine-chlorine bond, which is 242. Then I'm going to subtract 2 times a hydrogen-chlorine bond, which is 431. So when I do that math, I have it written down here, you get negative 184 kilojoules per mole. So the delta H of this reaction is negative 184 kilojoules per mole. All right, here's another example. Now for this one, it shows us why sometimes it's really important to draw out our molecules so we don't miss bonds. So each nitrogen has 5 valence electrons. We have 2 of them, so we have 10 total to account for. So I'm going to do nitrogen and nitrogen as a single bond. That's 2 electrons, 3, 4, 5, 6, 7, 8, 9, 10. That's all 10 electrons, but this nitrogen on the right over here, it only has 4. So instead, we move 2 of these lone pairs down, which gives us that triple bond. Now, diatomic nitrogen is always going to form that triple bond. We probably will have that memorized at some point, but just make sure you don't forget that, because the value of a nitrogen-nitrogen single bond is very different than a nitrogen-nitrogen triple bond. So we got to be careful with that. We have 2 hydrogen-hydrogen bonds, and we're making 2 NH3s, which each have 3 nitrogen-hydrogen bonds. So for my reactants, I have a nitrogen-nitrogen triple bond plus 3 times hydrogen-hydrogen bond minus my product. So I have 2 entire molecules here. So 2 times 3 bonds in each gives me 6 nitrogen-hydrogen bonds, which each have a bond energy of 391. So then when you do that math, you're going to get negative 97 kilojoules per mole. Another example here. So I'm going to draw these out first. So sulfur is one that can expand and its octet. Most likely, if you were given that one on a thermochemistry question, it would be drawn out for you. But when you fill in all of your electrons, you would notice that you had an extra 2 that you had to put right here. Okay, so for my reactants, I have 2 hydrogen-sulfur bonds, so 2 times 339, plus I then have 1 fluorine-fluorine bond, but 3 of those, so I have 3 times 155, minus I have 1, 2, 3, 4 sulfur-fluorine bonds, so 4 times 327, plus, and I have 2 hydrogen-fluorine bonds, so 2 times 567. When I do that math, I end up with negative 1,299 kilojoules per mole. All right, last one. This one's kind of lengthy, but I went ahead and drew the structures out for you. So for this one, in our reactants, we have 1, 2, 3, 4 carbon-hydrogen bonds, which have an energy of 413, plus 2 chlorine-chlorine bonds, which have an energy of 242, plus 2 fluorine-fluorine bonds, which have an energy of 155, minus, I'm going to pop down here so I have enough room. In this molecule, I have 2 carbon-fluorine bonds, which are 485 each. Then I have 2 carbon-chlorine bonds, which are 328 each. Then I have 2 hydrogen-fluorine bonds, which are 567 each, plus 2 hydrogen-chlorine bonds, which are 431. All right, so lots of multiplying, and then adding and subtracting, and I end up with negative 1,176 kilojoules per mole. Hopefully you got the hang of that. There'll be some practice for you to do, and I will see you next time.